Today we want to look at forces, and in particular we want to learn how to apply Newton's second law. Newton's second law, sum of the forces equals mass times acceleration. Remember that when we say sum, we mean summation, not sum as in a few of. So the summation of the forces, all of the forces, equals mass times the acceleration. So let's just look at a sample problem and see if we can think about how to work through Newton's second law. Let's say, for example, that we have a box sitting on the surface of a table or the ground or something. Let's make that a 5-kilogram box, and let's add a few forces. So let's say that there's someone standing over here pushing on the box, so they're pushing with a force of 10 newtons. Maybe there's a force of friction over here opposing the motion, I don't know, 2 newtons. And let's just say that's it. Let's say we want to think a little bit about how that box is going to move. Obviously, maybe the box starts with an initial velocity of 0, and let's say that we push on this so for a total of maybe 2 seconds consistently. Okay. Maybe a question is how far does the box go? How fast is it going? What are the things like that we could find? So the first thing always is going to be set a coordinate system. So if we set this coordinate system to be a regular upright Cartesian coordinate system, positive x is to the right, positive y is up. That'll help us think about what we're going to end up doing moving forward. The first thing we want to do is draw a free body diagram. So a free body diagram takes this object that we're interested in and sort of floats it out in space so that we're not worried about partner forces, and we'll just take that box out here and we'll identify all the forces on that box. So anything that says on that box. So obviously we have here 10 newtons pushing to the right. So we would say that 10 newtons is pushing on the box. Here we have friction is opposing motion. So there is 2 newtons opposing motion pushing to the left. We also know that gravity is pulling down. So gravity is pulling down, and we know that the force of gravity is what we call the weight. So the force of gravity is the weight of the object. In this case, force of gravity is equal to m times g. So in our case, if we want to calculate real quick, we could just say 5 kilograms times 9.8 meters per second squared, or 49 kilogram meters per second squared, or 49 newtons. So 49 newtons down, that's the weight. And then we also have, obviously, the table pushes up on the box pushes down on the table, but we're only really interested in the table pushing up on the box, and we're going to call that the normal force. Okay, and we're going to remember why do we like normal? Normal means perpendicular. So in this case, it's pretty obvious that normal is straight up because the table is parallel to the ground. But when we start slanting things, that'll be important. So we're just going to call the normal forces that contact force over here between the box and the table. So there's all our forces, and now we can apply Newton's second law. We remember that our coordinate system over here is a regular x and y coordinate system. So we apply Newton's second law twice, once in each coordinate system, because we remember to decouple things. So sum of the forces in the x direction, what do we end up with? We end up with 10 newtons, and that's to the right, and to the right is positive. We end up with 2 newtons, but 2 newtons is to the left, so that's going to end up being negative. That's the only thing going on in the x direction, so we're done. So that equals mass times acceleration in the x direction. We can do the same thing in the y direction, sum of the forces in the y direction. We have the normal forces up, so the normal force is positive, and we have the mg, or gravity, or the weight, is down. That's all that's going on in the y direction, so that equals mass times acceleration in the y direction. And now we can sort of plug in things that we know. We know that 10 minus 2 is 8 newtons equals, our mass was 5 kilograms times the acceleration in the x direction. So we can quickly calculate that the acceleration in the x direction is 8 over 5, and 8 over 5 is 1.6 newtons over kilograms is meters per second squared. So that's a pretty easy result. Over here in the y direction, if this thing is actually just sliding back and forth left and right, there is no change in motion in the y direction. So we end up saying, oh, the acceleration in the y direction is 0 because nothing's going on in that direction. So now my normal force is equal to mg, and we had calculated mg 49 newtons. So the normal force is 49 newtons. Not really necessary for this problem, but maybe it's interesting later. The table is pushing up on the box with a 49 Newton force. We should note that that's not a partner force, right? It's not that, box pushes on table with 49 newtons and table pushes on box with 49 newtons. This 49 newtons, the weight, is earth pulls on box, and this is table pushes on box. So table, earth, and box are 3 different things, so those are not partner forces. So now we have to go back and look at our original questions. We started with an initial velocity of 0, pushed for 2 seconds. This is all horizontal kinds of stuff, so really we just have a horizontal kinematics problem. We say v0 v(a)t delta x. We knew our initial velocity was 0. We know we're pushing for 2 seconds. And we now know that the acceleration is 1.6 meters per second squared. So we know 3 things. We can find the velocity and the distance. If we want to, say v equals v0 plus at, so it's going to equal to 0 plus 1.6 times 2, or the velocity is going to be 3.2 meters per second. That's a good final velocity for us. And we could say delta x is equal to v0t plus 1/2 at squared. Initial velocity is 0, so it's going to equal to 1/2 times 1.6 times 2 squared. So we're going to also end up with 3.2 meters. What a coincidence. Okay, so the thing travels 3.2 meters in 2 seconds, and in that 2 seconds it ends up being 3.2 meters per second. That's blind luck that those values turned out to be the same, but the process ends up working fine in that way. So that's a simple problem showing how to look at the problem, start with a free body diagram, identify all the forces, apply Newton's law in the x and in the y direction, find our accelerations, and then we go over to our kinematics problem. So 3 sort of steps in there, right? Free body diagram, apply Newton's laws, go back to kinematics in this case.